In this video, we're going to use what we used from the last video with implicit differentiation to help us find new derivative rules for other functions that we haven't yet found. If you want to follow along, the links to the companion worksheet are in the description below. So let's get started. Now up till this point, we only know the derivatives of some functions, but not all of them. And so looking at this first problem, we don't know what this derivative is, y equals ln of x. And so at face value, we can't do this. But because we now have implicit differentiation under our belts, now we can use that idea to help us with this. How do we do that? Well, we recognize that ln, again, we don't know the derivative, but we do know its inverse function. Its inverse function is the function e. And so if we were to write this, instead of writing ln on this side, we can write e to the y equals x. Now e, since we do know the derivative, we can find the derivative here. And so to do that, we're going to use implicit differentiation because y isn't by itself. It is here, but can't find this derivative since we don't know it. But all we've done is we've just rephrased this same equation in a different way that allows us to find the derivative. So the derivative of this is going to become e to the y times dy dx equals, and then the derivative of x is 1. And so to get dy dx by itself, we divide by e to the y. So dy dx equals 1 over e to the y. Now notice that here y was in terms of x explicitly, and so we could leave it like this, but we want our derivative to be in terms of x. So to do that, what we'll do is we will substitute out y for what it equals. It equals ln of x. So 1 over e to the ln of x. Now, since e and ln are inverse functions, they cancel each other out. So that leaves us with 1 over x. And that is the derivative of ln of x. And that's how we come up with it with implicit differentiation. All right, so let's try another one. Another problem is arcsine. Now, arcsine is the inverse function of sine. So to rewrite this, we would write it as sine of y equals x. Again, this and this are equivalent statements, but now we can take the derivative of this with implicit differentiation, but we can't with this. So the derivative here, derivative of sine becomes cosine of y, let's put parentheses around those, times dy dx equals 1. So now we'll divide by cosine of y. So dy dx equals 1 over cosine of y. And then we'll replace y with arcsine. So 1 over cosine of arcsine of x. Now, unfortunately, we can't resolve this as simply as we did up here in number 1, as e and ln were inverses. These two aren't inverses. So how do we do this? Well, off to the side, what we're going to need is we're going to need ourselves a little right triangle. And so what we're saying right here with arcsine is that keep in mind that with all trig functions, you plug in an angle and get a ratio. But this is an inverse trig function. So we're not plugging in an angle, we're plugging in a ratio and getting back an angle. So this right here, this is our angle, arcsine of x. So what's the ratio? Well, the ratio is sine. And so we could think of that as x, so the opposite side is x, and the hypotenuse is 1. Now, what we want is we want cosine of this angle. Well, we have the angle, so to get cosine, we need the adjacent over the hypotenuse. So, using Pythagorean theorem, we get 1 minus x squared is the length of our adjacent side. And so cosine is this over 1. So we have 1 over the square root of 1 minus x squared. That's the cosine ratio of this angle. And so that is the derivative of arc sine. Now it's completely back in terms of x. Let's try another one that's similar. This one it's written in a different format, but it's the same idea. Oftentimes you'll see cosine inverse written this way. Sometimes you'll see it written as arc cosine. Same idea. So first, we're going to rewrite this as cosine of y equals x. And so when we take the derivative, this becomes negative sine of y, put parentheses, times dy dx equals 1. We'll divide negative sine of y over, so dy dx equals negative 1 over sine of y. We'll replace y with cosine inverse. So sine of cosine inverse of x, like that. So again, as with the previous problem, we'll set up a right triangle. The angle in question is cosine inverse of x. So what that's saying is that x over 1 is our cosine ratio, and we need sine. So to get that, we use Pythagorean theorem to find the third side, and so we have 1 minus x squared. So our derivative is, in terms of x, negative 1 over square root of 1 minus x squared. So now, number 4, very similar, except now we have a 3x inside. So when we rewrite this, we're going to have tangent of y equals 3x. And we're going to see what effect that 3 has when we take the derivative. So the derivative of tangent of y, parentheses, is secant squared of y times dy dx. The derivative of 3x is 3. So we'll divide secant squared over, so dy dx is going to equal 3 over secant squared of y. Now, remember that secant is the reciprocal of cosine. So we can simplify this by saying that instead of dividing by secant, we can multiply by cosine squared. And so we'll replace y with tangent inverse of 3x. Now this one's a little more complicated, but we still have to start with a right triangle. So our angle in question is tangent inverse of 3x. And what we're saying here is that our tangent ratio is 3x. So tangent is opposite over adjacent. So we have 3x as our opposite side. And we always use 1 as our denominator. That's kind of the theme we're working with. And so what we want is we want cosine. So we're going to need the hypotenuse. So using Pythagorean theorem, this squared plus that squared, we have 1 plus 9x squared for our hypotenuse. So we have 3 times, now the cosine ratio is 1 over that. So 1 over the square root of 1 plus 9x squared. But don't forget, it was cosine squared, so that quantity is squared. So that means we square the top, that stays as 1. We square the bottom, and the radical goes away. So we're left with 3 over 1 plus 9x squared. So for our final example, now we're looking at arc cotangent. similar to tangent inverse. So what we do is, again, we write this as cotangent of y equals x squared. When we take this derivative, implicitly it becomes negative cosecant squared of y times dy dx equals 2x. So we're going to divide by negative cosecant squared of y, leaving dy dx alone on the left. Negative cosecant squared of y. And like the previous problem, we're dividing by cosecant squared, but cosecant is the reciprocal of sine. So to simplify this, instead of dividing by cosecant, we're going to multiply by sine. And so we replace this. We replace y with the expression arc cotangent of x squared. So finally, that's going to be our angle, arc cotangent of x squared. Now, cotangent is the reciprocal of tangent. Tangent is opposite over adjacent, so cotangent is adjacent over opposite. So the adjacent side is x squared, that's over 1. Now we want sine of this right triangle, so we're going to need the hypotenuse. So that's going to be square root of x squared, squared, so that's x to the 4th, plus 1 squared, which is 1. So sine, the sine ratio is going to be, well, remember, our angle is right here, so it's going to be the opposite over the hypotenuse. So 1 over square root of x to the 4th plus 1. But remember that it's sine squared, so this quantity will be squared. So we square the 1 and we square the radical x to the 4th plus 1. So that leaves 1 on top, and we bring up the negative 2x all over x to the 4th plus 1 for our denominator. So a rather complicated derivative, but thanks to implicit differentiation, it allows us to make this possible. Without implicit, this could not be done. If you liked the video, please give a thumbs up. For more videos like this, click the subscribe button. If you have suggestions or problems you want to see worked out, type a comment below. To support the channel, click the Patreon link to help keep this going. Thank you so much for watching. Remember, the only way to understand something is to do it.